Alright, so this video will be covering items 24 through 31 on the outline for your semester final. So this is going to include a lot of Unit 3, a lot of the math part. So we'll start with empirical formulas. We'll go back into Unit 2 a little bit and do some naming, and a lot of conversion, and we'll end with stoichiometry, just basic stoichiometry. But then we'll pick up some more stoichiometry with limiting reactants and excess reactants on the last little video. So here we're going to start. Most of this is just math, and we have examples of almost all of these. So determining an empirical formula on the in-class review is example number 11. So to determine empirical formula, remember that the empirical formula is the reduced formula. So this is not what 11 is, but if you were given something like this formula, the empirical formula here would be C1H3O4, because you can divide each of them by 2. And so it's the simplest formula that can be formed. So that's what we're going to do with this math. So if you remember back when we did empirical formulas, first of all, you need to get element analysis. You need to have the amounts of each element that are involved. And so we want these in grams so that we can convert them to moles. However, if they're giving you percentages, we're going to assume we have 100 grams. We talked about percentages earlier. It doesn't matter how much you have, the percentages are going to be the same. So if we assume we have 100 grams and 71.65% of it is chlorine, we have 71.65 grams of chlorine. So the same thing will happen for the carbon and the hydrogen. Okay, so the next step, once you have the grams of each, is to convert these all to moles. So a little quick calculation using the molar masses. Okay, and so when you're doing this, I don't know what you all were told, but we're not looking for any kind of significant figures. We're looking for a formula in the end. So it really doesn't matter how many digits you give, but you want to make sure not to round away your answer. So keep a couple digits, just so that you don't end up rounding away the subscripts that happen. So if we do all of these, there's nothing special about the number of digits I'm doing. Okay, and once you have moles of each, the next step is to take each one of these and divide it by the smallest number of moles, because you're looking for a ratio between each element, and you want the smallest one to be a 1, like I just showed you on the empirical formula. You want to divide down if you can. So we're going to divide them all by 2.0208. Okay, that's the smallest one. Alright, so if you go calculate these, you'll get essentially 1 for this first one. So you need to be able to interpret this. So this comes out, the calculator is 1.000148. It's not perfect at 1, but it's pretty darn close. So that's going to be subscript for chlorine. Obviously carbon's going to be a 1 because you're dividing it by itself. And then you could probably tell from the next one that you're going to have 2 hydrogens. Okay, so these are all your subscripts. So the empirical formula is going to be ClCH2. And it doesn't matter which order you write those in. There's a way that chemistry people are going to do it, and that's not it. But it doesn't matter as long as you have the ratios right, that you have the subscripts right. So this is the empirical formula. And then the molecular formula it asks you to find. So the molecular formula is the unreduced. So they have to give you another piece of information to be able to do that. And that's what this molar mass is for. The molar mass is the mass of the entire chemical when it was unreduced. So what you have to do to figure that out is to go find out how much your molar mass weighs. Or your empirical formula weighs, sorry. So you're going to add up all of those that are in this formula, which your formula right now adds to 49.48. But they told us that the real one weighs 98.96. So most of you will probably be able to see what you're going to have to multiply it by. But if you don't, if you take the big number and you divide it by the small number, it will tell you how to unreduce that, what to multiply by. So what that's saying is we got to multiply every one of these subscripts by 2. So the molecular formula will be Cl2C2H4. Okay, and then this is the molecular. Okay, they are the same formula, just one has been reduced, so one is simpler mathematically. So that's empirical molecular formulas. We're going to go back in a little bit to Unit 2 about naming. So remember, when we're doing naming, you got to identify whether it's ionic or covalent to start with. If it's ionic, we don't use prefixes, but we can possibly use Roman numerals. If it's covalent, we're using prefixes. So I'm just going to go through these 6 really quickly and put an I or a C next to them so that you know whether we're using prefixes or not. So remember, if there's a metal and a non-metal, you've got ionic. So we've got ionic, 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 covalent, covalent. So on E and F we'll be using prefixes, on A through D we will not. But you also need to be aware on that first element, the metals, if it's from anything in the transition elements, we're going to need a Roman numeral. So if you look at these guys, we're going to need a Roman numeral for this one. Oh, sorry, nope. This one. And this one. Why we didn't need one for silver, even though it's in the transition elements, is that silver is one of those ones that I told you you'll have to memorize, that you know its charge. So we got 2 that we're going to use Roman numerals for. So we're going to give these names. The name of Ag is silver. And then remember that for the negative, we're going to take the original name and end it with "ide", so that's silver sulfide. Okay, for the next one, we've got manganese. And we've got oxide. However, we need a Roman numeral because Mn is in that transition elements and we don't know its charge. So we're going to have to figure out what its charge is by who it's paired with. So you have to pay attention. You have to know O's charge. So oxygen from the periodic table, if you look it up, will have a -2 charge. But we have 2 of them, which means we have a total of a -4 charge. So manganese has to balance that out. So manganese is going to have to be a 4 charge. Use Roman numerals. Sorry, that's a little squished. It's an IV for Roman numeral 4. Okay, for letter C, the name of the positive one is potassium. We don't change that. And then that second thing is a polyatomic ion. So this is not one of the ones you were asked to memorize. So on a review, it's fair game because you can look it up. On the test, you'll be limited to the ones that you were asked to memorize. There should have been 10 of them. But MnO4 is called permanganate. Okay, we didn't need a Roman numeral, just that. Okay, so then on D, the name of Cu is copper. Name of I is iodide. Negative is going to become iodide. Okay, but we have to give a Roman numeral here. So we have to figure it out from iodine's charge. So iodine is a -1 charge, which means a total, since we have 2 of them, we have a -2 charge. Copper has to balance that out by being a +2 charge. Okay, so we get copper 2 iodide. So for for E and F, when they're covalent, we don't have to use Roman numerals at all. We don't have to know polyatomics. We're going to use prefixes. So this one's going to be phosphorus, penta, or 5, chloride. Still going to end the second one with IDE. Now, there is a prefix for 1, but if the 1 was a leading one, we don't have to put it. We don't have to write monophosphorus if it's out front. If it's not out front, we do have to write it. Okay, so the next one looks a little like a mess, but we're going to use prefixes. So we've got dinitrogen, not changing the name of the first one, and then penta, oxide, and then this water attached, that's a hydrate, if you remember. So we have 4 of them, so we're going to go tetrahydrate. So that's a mouthful, but that is dinitrogen pentoxide tetrahydrate. Okay, so that's one way, is you have to come up with the names if I give you the formulas. The other way is, can you give the formula from the name? So you have to pay attention. If you're given prefixes, you don't have to pay attention to charges because it was covalent. If you're not given prefixes, you have to do charges because it's ionic. So on A, sulfur difluoride should be SF2, and that's it. We had 1 sulfur and 2 fluorines. No charges. But on B, C, D, and E, there are no prefixes other than with the hydrate. We're going to have to pay attention to charges, so you really have to know these. So if you look up lithium on the periodic table, you'll see it's a +1. If you look up nitrogen, its name got changed to nitride, but it's nitrogen, it would be a -3. So So I don't know how you guys did this, but shortcut cheat is to crisscross these charges unless they already cancel out. So you would get Li3N1. Okay, for iron 3 chloride, again, no prefixes. We got to pay attention to charges. So iron is Fe. It's in that group that doesn't, or in the transition elements that we don't know their charges, but that's why they were given the Roman numeral. That's its charge. And then chloride, when you look it up, is a -1. So those don't match, so we can crisscross their charges and get FeCl3. Okay, ammonium acetate, those are 2 polyatomic ions, no prefixes, so we're going to have to go look those up if you don't know them. Ammonium is NH4+, and acetate is C2H3O2 negative. Those charges already match, so we just have to smush them together. Okay, so that's ammonium acetate. And the last one is sodium sulfate heptahydrate. So sodium, if you look it up, has a +1 charge. Sulfate periodic is a polyatomic ion. We look it up, it has a -2 charge. So when you put these guys together, we're going to crisscross their charges because they don't match. Okay, and then we have a water attached. We're going to go dot and then hepta. We're just going to put 7 H2O. Okay. So those are our naming. Those will mostly be multiple choice questions, being able to match them. So pay attention to whether you needed prefixes, or you needed Roman numerals, or you had to pay attention to charges, or what's going on there. Okay, next up is about molar masses. So molar masses, I think we should all be pretty good with now. I'm going to just do B and C. You can check the answer for A. But B and C are a little more complex, so I just want to make sure that you can do this. So you don't have to show the work for molar masses because we do it so frequently. But I'm going to show it for B just to make sure you understand what we're doing. We have 2 Ks in this formula, so we have 2 times 39.1. We have 1 Cr, which is so 1 of the 52. Okay, I'm going to do this a little long-winded. So next we hit 4 oxygen, so we have 4 times 16. Okay, and then this little dot does not mean times. It means that it's attached to. So it's attached to 3 waters. So we're just adding the 3 waters on. So if you're doing this, we're going to add on, we have 6 hydrogens, and we have 3 oxygens because that 3 goes with both of those. The other thing you could do is instead of doing 6 hydrogens and 3 oxygens separately is you could look up the mass or find the mass of water and just do 3 of water. Okay, so I just want to make sure you could do the mass of a hydrate. Okay, and I'll add this up. And you should get 248.25, and the units of molar mass are always grams per mole. Okay, so on the part C, I just wanted to make sure that we were good with distributing this 3 on the outside, that we understood that 3 goes with everything inside. So when you're adding up the molar mass here, you should do 3 times the nitrogen. Okay, and then there are 12 hydrogens, because we have that 3 goes with both of those, so we have 12 times the 1.008. Okay, then we have the phosphorus, which is 30.97. And then we have 4 oxygens, so 4 times the 16. So that's what you should be adding up in your calculators. Okay, and the molar mass I got is 149.10 grams per mole. Okay, and if you're going through this and you're wondering why I'm cutting off decimals that my calculator gives me, I'm using the numbers from the periodic table and doing sig figs, so since we're adding, I'm doing least number of decimal places, and I'm giving 2 decimal places here. Okay, so those are molar masses. I feel like most of us are probably pretty good at that. So the next step was balancing chemical equations. Okay, so I have a couple equations for you to balance, and we've done a lot of these. So these are mostly just guess and check. They can be difficult, they can be easy. It just depends on what you've got. We'll look at that first one. If I were you when you're balancing these, I would try to find the things that only occur once and balance on each side and balance those first, and then do the other elements. So if you're looking at A can be a giant mess, but I'm going to ignore oxygen right now because oxygen is in every chemical altogether. So that's going to be super rough right now. So potassiums, we're good on those. Okay, hydrogens, we've got 2 over here and we've got 3 over here. So that can be a little bit of a trick. Okay, and so there's a couple ways to approach this. I would say, okay, whatever's on the left, whatever I put in front of here, it's going to end up being an even number because you've got, you're multiplying by the 2. So this guy right here, this hydrogen right here, is causing it to be an odd. So I'm going to go ahead and put a 2 here just to change that to an even to make it an easy multiplication. So if I do that, I've messed up my case. So I'm going to go back and fix my potassiums. Okay, so now that makes me have 2 hydrogens here and 2 more hydrogens here, so I have 4 hydrogens. So I'm going to put a 2 right here and balance my hydrogens. Then I'm going to look at my oxygens. So if I look at my oxygens, I have 4 oxygens here because I have 2 times 2, and then I have 2 more oxygens here. So I have 6 oxygens on the left side. If I check the right, I've got 2 here, I've got 2 here, and I've got 2 here. So that gives me 6 oxygens on the right side, and I'm balanced. Okay, but these guys can take a long time or a little time, so you just need to practice getting a way down to balance these. Okay, so on B, if you were balancing this one, I would treat NO3 as an entire blob, like it's a one thing, and not balance my O's separately like that. So the only oxygens that I'm going to balance as oxygens are here and here. I'm going to treat NO3 as a whole blob. And so if I'm looking at this guy, I'm going to balance my irons. They only occur once, so that's pretty easy to put a 2 right here to balance my Fe's. Okay, my oxygens, if I only focus on the oxygens, I've got 3 over here. I could put 3 here. I may have to go back and erase, but now I balance my oxygens. Okay, as far as my nitrates, if you look at the things that are highlighted, I've got 1 of these over here, but I've got now 6 of these on the right side. So I've got 6 of those over here. So I can fix that by putting a 6 out front. Okay, and now I would go to my H's, and now I see my H's. I've got 6 H's over here, and I've got 6 H's over here. And so those are balanced. So if you get a polyatomic ion, I would treat the polyatomic ion as if it were one element and go with that. Okay, so it keeps it a little easier because then otherwise you're going to have O's in a lot of places. So this shows up again on C. If you look at C, if you're trying to balance the O's, they look like they're all over the place. But if you treat NO3s as an entire blob and then SO4s as a completely different blob and just try to balance the yellows and the pinks, it may work a little easier. So I'm going to start off and balance my silvers, my AGs. So I'm going to need to put a 2 right there. Okay, then I'm going to balance my yellows, my nitrates. So I have 2 NO3s on the left side, so I'm going to have to put a 2 for the NO3s on the right side. Okay, then I'm going to do my H's, and I've got 2 H's on the left, and now I have 2 H's on the right. And then my pinks, my SO4s, are already balanced. Okay, so come up with a way that you can go through and balance these guys. Okay. All right, next up is mass percent. So you have to remember that mass percent, we already did it once, is part over the whole times 100. So here I'm telling you that I want the mass percent of carbon. So that's the part that I want on top, and the whole is just going to be the whole chemical. So you were given no real numbers in here. So the numbers that you have to use are from the periodic table. So I showed you one earlier with ammonia where you were given numbers in the problem. Then I showed you it was the same answer when you use the numbers from the periodic table. So that's what we're doing here. So I'm only going to do A here, and you can probably do the rest of them and you'll see the work. So the percent of carbon here, in this formula we've got 8 carbons, so we're going to have 8 times the 12.01 as my part, and then to do the whole you've got to add up this entire thing. So 8 times 12.01 plus 10 times 1.008 plus 4 times 14.01 plus 2 times 16. So this whole thing I've got weighing 194.2. And then we'd multiply by 100 to make it a percentage. Okay, and then we're going to go ahead and calculate it. And the percent of carbon here should be 49.47%. Okay, you would repeat the process on B and C, so just the amount of carbon over the whole mass. So you can check those answers on course sites if you want to see the whole thing worked. Okay, so the next thing up was, can you convert between units if it was just one chemical? So can you get everything to moles and then convert from particles to liters of gas to grams, whatever I'm asking you to do? So on A is asked you to find the number of formula units and 87.6 grams of lithium perchlorate. Formula units is a particle. It's just the word we use for particles for ionic. chemicals. So LiClO4 is an ionic. We use molecules for covalent and atoms for individual elements. So this is just particles. So we're going to start off with 87.6 grams of the LiClO4. Okay, so the first thing that we've always got to do is get the thing to moles. So we're going to use the molar mass. So you got to add up the molar mass of lithium perchlorate. Okay, so I have 106.39, and that's per 1 mole. Okay, and then since we are not done, we have to go to formula units. Grams are going to cancel. We need to use Avogadro's number to get us 2 particles. So we need to cancel out the mole and get the particles. So 6.022 times 10 to the 23rd. And this would be atoms or particles or molecules or formula units. I'm going to abbreviate it. That's not me cursing at you. That's abbreviating formula units. And now our moles will cancel. And so we should end up with formula units as our answer. So now we can just go ahead and calculate. Okay, and we definitely want to do significant figures, so we're going to go from the numbers given in the problem. So I'm going to give 3 significant figures. That's going to be 4.96 times 10 to the 23rd. And this would be formula units of LiClO4. Okay, we'll skip around and just do a couple of these. We'll do C, D, and E. I'm going to skip B. I think you could do that. That's just going from grams to moles, but I want to make sure I see some different ones. So on C, asks you to find the number of liters of gas at STP, 4.65 times 10 to the 23rd molecules of H2. So you'll see H2 is covalent. That's 2 nonmetals together. We called it a molecule instead of a formula unit. Okay, minor detail, but that's just why those different terms are coming up. So we're going to start with molecules, and forgive me, I'm going to shortcut molecules as MC just so I have enough space. So first thing is to go to moles, so we're going to do Avogadro's number is 1 mole of hydrogen. Okay, so that's going to cancel out my molecules. And then I'm going to liters of gas at STP, so that's not molarity, that's the one time you get to use this 1 mole of hydrogen is 22.4. Do not use that unless it says STP in the problem. You will learn later on in the year where that 22.4 comes from. It comes from a gas law. And we're just kind of cheating and giving you one number right now, so only for a particular temperature and pressure called STP do we get to use that. Okay, so if you go ahead and calculate that, we have liters as our units because our moles cancel, and you should get 17.3 liters of the hydrogen. I did 3 sig figs because that's what I was given in the problem. Okay, so I'm going to do E right now and then come back to D because D has a little wonky thing, but I want you to see the difference. E asks you to find liters again, but it doesn't say anything about STP. Instead, it gives you molarity. So this, you're not using 22.4 at all. Okay, you've got to use this molarity. So I'm going to work it like you guys were taught. So first thing we're going to do with that 28.9 grams is to convert that to moles. So we need to know molar mass. Okay, so molar mass is 56.11 grams per 1 mole of KOH. Okay, the next thing up, we've got to get rid of moles and get to liters, and so that's where we used the 22.4 when it was at STP. But remember, this guy is 0.25 moles per 1 liter. So you just have to orient that so that your moles cancel out. So we're going to put the 0.25 moles down here and the liter up there, and that will get us our moles to cancel. Okay, and we'll go ahead and calculate. Okay, and you should get 2.1 liters of the KOH. Okay, because this one has 3 sig figs and this one has 2 sig figs, so we're going with a lower number given in the problem. So 2.1 liters. Okay. So I just want you to see the difference between liters. If they give you STP, you're using 22.4. If they're not, they're going to give you molarity, and you're going to use that one. Okay, so D is a little tricky. It asks for the number of oxygen atoms and 48.6 grams of phosphoric acid. So at first it looks just fine. So it looks like we're going from grams to particles, just like we did in A. And we are definitely going to do this, so we need molar mass. Okay, so the molar mass here is 97.99 grams per 1 mole of H3PO4. Okay, now you can do the next part two different ways. I'm just going to pick away and go with it. So the next thing that most of you guys would think about is, okay, we're going to go 1 mole of H3PO4 is 6.022 times 10 to the 23rd. And that's a covalent compound, so we're going to call it molecules of H3PO4. Okay, so that's exactly what we did in question A. But this one asks for just the number of oxygen atoms, and what we've done is find the molecules of H3PO4. So we're looking for just a part of this particle. So we have to keep going, and so we're out of just normal conversions that we know. We have to look at this formula. So if you look at one of these things, you can tell how many oxygen atoms are in there. So I'm going to make up this conversion from this formula that says 1 molecule of H3PO4 is going to have 4 atoms of oxygen. And I'm simply getting that from right there, that there are 4 oxygen atoms in that. So only when it asks you for a part of that particle are you going to have to look at and rip apart that formula. Okay, so then you can go ahead and calculate it. Okay, and we're going to do 3 significant figures. So we get 1.19 times 10 to the 24th atoms of oxygen. Okay. Alright, so that is basic conversions in stoichiometry. We haven't done the mole-to-mole ratio. The last problem I'm going to do in this little video is this big long one, this combustion analysis stuff. So this one is rough, and what I do may be a little different from what you were taught. This is the way that I taught my kids, and this is where I found is the simplest way that I can get across to them. So we have a compound containing only carbon, hydrogen, and oxygen. It says combustion of 10.68 grams of the compound produces 16.01 grams of CO2 and so much water. The molar mass of the compound is 176.1. What are the empirical and molecular formulas? So we did empirical formulas the first problem in this little video. The goal was you needed to get grams of each element so you can convert them to moles. So this next part that I'm about to write, you don't need. I just want you to have an understanding. So whatever this compound is, we are combusting it, which means we're adding oxygen, and then we are going to make carbon dioxide and water. You cannot balance this equation and do any stoichiometry with this because you don't know what the formula for this compound is. You do know that it has carbon, hydrogen, and oxygen in it. You just don't know the subscripts. So, but they did tell you that there was 10.68 grams of this guy, and you made 16.01 grams of carbon dioxide and 4.37 grams of water. So from what we did earlier, you can clearly tell that there's got to be some oxygen number, and you could figure out what that is from the conservation of mass. However, we don't need that number. We need the number individually of those 3 elements. So here's what I do. Okay, we need the grams of carbon, the grams of hydrogen, grams of oxygen. Well, I don't know the grams. I can't pull out the grams of carbon from that formula because I don't know what it is. But what I could do is look at this formula right here, and if I could find the grams of carbon in this formula, I know that all the carbon from carbon dioxide had to come from this compound because it sure didn't come from oxygen. So I can say that mass of carbon had to come from the original. It's the same mass. So how I'm going to pull out the mass of carbon is do a proportion. Okay, and so you guys, I think you were taught something that said new over old equals new over old. And so for this guy, the olds are going to come from the periodic table. And so if you do new over old, we were given a new number of carbon dioxide, but our old was from the periodic table. If you look up that molar mass, it's 14.0 or 44.01. So on the other side, we would need our new grams of carbon, okay, and our old grams of carbon from the periodic table in carbon dioxide are 12.01. Okay, so if you go ahead and cross multiply that and solve for x, you get 4.369 grams of carbon. Okay, so if there's 4.369 grams of carbon in carbon dioxide, it had to come from over here. So that's what we're going to use for our grams of carbon. So we're going to do a similar process for hydrogen, because if we can find out how much hydrogen is in this water, we can say it came from here. Okay, so we're going to do that same thing. We're going to do new over old equals new over old. So the old comes from the periodic table. So if we do new water which is 4.37 grams, over periodic table water, that's 18.016 grams. We want to know new hydrogen. Sorry, I should label this as hydrogen. And this is water. Okay, we want to find out new hydrogen. And then the old hydrogen that came from the periodic table is 2.016. Sorry, this is water. Okay, 2.016 grams of hydrogen, because in that formula, when you added that up, there are 2 hydrogens in there. So if you cross multiply here and solve for that X, you're going to get 0.489 grams of hydrogen. Okay, so that's great. And then you would think, okay, well, I'll do it again for oxygen. You cannot do it for oxygen because you can't use either of these formulas, because this compound had oxygen, but so did this. So you don't know which of these oxygens or how much oxygen from each compound went from the original or what came from the combustion part by adding the oxygen. But you do have one more number that you know this whole thing altogether weighs 10.68. Well, you've already figured out the grams of carbon and you figured out the grams of hydrogen. Those don't add up to 10. The missing piece has to be oxygen. So to find the oxygen, we're going to take 10.68 and we're going to subtract the carbon and the hydrogen added together, so that the rest of it has to be the oxygen. Okay, so 5.822 grams of oxygen. So I have not been doing sig figs at all on this. I may have accidentally got some of them, but we're looking for a formula in the end, so I don't really care. I'm just trying not to round away my answer. So that's the hard part of combustion. From there, you can do it like any other empirical formula problem. So empirical formula says once you get grams, we're going to convert them all to moles. Okay, so we're going to set this up. Okay, so if you calculate this, you should get 38 moles of carbon and 0.4851 moles of hydrogen and 0.3639 moles of oxygen. Okay, so once we're at moles, we're supposed to find the lowest number and divide everybody by that. So 0.3638 is my lowest number. Okay, so this guy's obviously going to be a 1 for carbon, and this guy's going to be a 1 for oxygen. But you've got to be really paying attention on this middle one. If you divide this, you will get 1.333. That does not make 1, and that doesn't round to 2. We're going to leave that as 1.33. But we're going to have to do an adjustment here. So what you would write down as your formula would be C1, H1.33, and O1. Well, you've never seen a chemical formula with a decimal in it, so we have to get rid of it. So some of you may do this before you write in a formula. I just want to show you why we're doing this. So you have to get rid of this. Well, whether you're a decimal person or a fraction person, this is a 1 1/3. Or 1.33, you have to get rid of that decimal, and the only way you're going to get rid of that decimal is you're going to have to multiply it by something. So how we get rid of a third is we multiply the thing by 3. But if you multiply this guy by 3, you have to multiply all of them by 3, so you keep the ratios the same. So if you do that, you're going to get C3 H4O3. 1.333 times 3 is 4. Okay, so this is your empirical formula. Okay, so the other thing that you were asked to do was find the molecular formula. So we talked about that earlier, that you have to have the molar mass. So you were told that the whole thing weighs 176.1. You have to find out what your formula weighs. So you have to add up the 3 times 12.01, the 4 times 1.0008, and the 3 times 16. So our formula right here that we've gotten weighs 88.06, and they told you the real thing weighs 176.1. So we talked about you would divide the big one by the little one if you can't tell what it's going to be. This guy's going to be a 2. And so that's what you would multiply your whole formula by. So we'd get C6 H8O6. So this right here is your molecular, which is unreduced. Okay, and that's it for this section.